the group. Here is, got it. Here is a group. It's got two generators, A and B. A to the fourth is B to the fourth is the identity, and it's not an abelian group because B times A is not A times B. In fact, some of you may recognize that as the semi-direct product of C4 with C4. So I don't know how to draw pictures of non-abelian groups. Now, good. There we go. Now I'm going to take a subset of that group. It has 6 elements. And that subset is a different set in G. It's got parameters 16, 6, and 2. What does that mean? Well, we look at all the differences, in quotes, they're really quotients, x times y inverse, as x and y go over all distinct values in the subset. So 6 times 5 quotients, or differences, x times y inverse, and we write down all of those, and it turns out that we get every non-identity element in that group of order 16, all 15 of them, exactly twice. 6 times 5 is 15 times 2. So magically, we're covering every non-identity element of the group the same number of times. For example, if you say, show me where you get the difference A times B cubed, well, it's element A of the subset times element B inverse. It's also, yeah, there we go. And it's also element B times element AB squared inverse. Now, from that, we are going to take an element in the group ring by going to the subset, and we want to throw all of these into our expression with a negative sign, and every other element of the group, the other 10 that we're not seeing in the subset, those with a plus sign. And we add them all up, that lives in the group ring. Now, let's take that element, the same one I just showed you. Now I'm going to form d to the minus 1. What does that mean? It means for every summand, take the inverse. So that minus a squared b cubed is going to turn into a minus the inverse of a squared b cubed, and this plus b cubed will turn into plus the inverse of b cubed, and so on. So invert every summand. That's d minus 1. And now do a calculation. Calculate, as a formal expression, d, the 16 elements, times d to the minus 1. So that's 256 products. And you're going to get, those will all be expressions in the group ring. Well, it turns out that all of the cross terms are going to disappear. The only things that will be left are every element times its own inverse. So that's going to be, really that should say 16 times the identity, but I'm being lazy and I'm abbreviating that as 16. So d times d to the minus 1 is an expression in the group ring, but every coefficient of every non-identity group element has gone away. Okay? Well, that's equivalent to the property I told you before. A subset of a group of order 2 to a power of 2 is a different set in the group if and only if, when we make the group ring element in the way that I just showed you, we get this equation satisfied. Now, we're going to use that later, but first of all, why are we doing this? So why are we studying different sets? Well, different sets lie at the intersection of a lot of subjects that are the topics of this conference: design theory, coding theory, graph theory, finite geometry. Different sets have been studied for a really long time. And there's different sets in abelian groups. Those have applications. They have applications in signal design, such as synchronization, radar, optical image alignment, coded aperture imaging, many applications. Also, if we take different sets in non-abelian groups, well, amongst other things, we can use them to construct Hadamard matrices. In fact, one of the most promising approaches to a potential resolution of the Hadamard matrix conjecture is based on a variant of a different set in a non-abelian group. I'm referring to Ito's conjecture if you are an expert on Hadamard matrices. So these are important both in the abelian and the non-abelian setting, and we study them using a variety of tools, principally algebraic number theory, character theory when there's something abelian, and representation theory when we're non-abelian. Now, I'm interested for this talk in groups whose order is a power of 2. Now, why am I restricting to order a power of 2? Well, those groups whose order is a power of 2 are a very rich source of two things. The first is groups, and the second is different sets. So first of all, groups more than 99% of the isomorphism classes of groups of order at most 2000 are accounted for by orders of power of 2. In fact, just order 1024 will do that for you. So the vast majority of groups of smallish order are actually groups whose order is a power of 2. And given that there's so many of them, it's not really surprising that's a great source of different sets. So that's where we're going to be living, in groups of order 2 to the n. And I can tell you something about the parameters of different sets that live in those groups. So up to something that is not terribly important, a complementation. I said about order a power of 2. It actually has to be a power of 4. So this list goes on, but I can just have a general parameter 4 to the d. So we must be, if we're going to be in a group of order 2 to the n, it must be a power of 4. And I can then tell you, this is just the d that I'm counting up, I can then, that determines the size of the subset. We saw 16.6 a moment ago. And it tells you also the repetition count, which previously was 2. So if you just do the sums, you work out that that's how many times you must be seeing each non-identity element of the group. Okay, so those are the parameters that we're interested in. And a different set with those parameters is called a Hadamard different set because of the connection with Hadamard matrices. So far, so good. Marvelous. What are we trying to do? We are trying to determine exactly which isomorphism classes of groups of order 4 to the d contain one or more different sets. There is a secondary objective, which is to say how many inequivalent different sets. I'm not interested in that today. I just want to know for every group whose order is a power of 4, does it contain a different set? And not only existence, I want this thing in my hand. I want it explicit and constructed. Especially these orders. 4 is trivial, 16, 64, and 256. We'll see why in a moment. And just to mention, it seems that answering that question becomes more difficult as the exponent of the group gets larger. Now, remember I said that there were 4 non-student co-authors on this work. I'd like to know if anyone can tell me something that we all have in common. Here's the first clue. This is John Dillon. This is Jim Davis. This is me. And this is Bob Liebler. Oh, I beg your pardon. Sorry, this is Ken Smith, who co-wrote a paper. Sorry, reading incorrectly. This is Ken Smith, who co-wrote a paper with Bob Liebler. So can you see we're all obsessed with this subject? We've been obsessed all our mathematical lives with different sets, particularly in groups whose order is a power of 2. And you might politely wonder why we haven't finished this problem off yet if we've spent collectively so much of our lives on it. So why is this so difficult? Well, maybe it's because we're not very smart, but perhaps there are other reasons as well. So the first problem is this. Okay, if you want to tell me which groups of order 4 to the d contain a different set, the first thing you've got to tell me is, what are the groups of order 4 to the d? Not so easy. Determining all the isomorphism classes of groups of a fixed order is an old and extremely difficult problem. It goes back to the 19th century. And a lot of extremely smart and knowledgeable people have worked on this. Before modern computers were available, all the calculations were done by hand, and there was detailed case analyses depending on how the order of the group factorized, and it was really, really easy to make mistakes. Again, not because these people didn't know much, but because the problem's so hard. So we do have modern computer algebra systems, especially GAP and Magma, that have removed a lot of the errors and have enabled us to go way beyond anything that will be possible by hand. So let's take a look at what we know about groups of order 4 to the d, the isomorphism classes. So every undergraduate algebra student, I hope, would be able to tell us that there are exactly 2 isomorphism classes of groups of order 4, C4 and C2 squared. How many groups of order 16 are there? Well, if you want to know that, you're going to have to go to an advanced textbook on group theory. Turns out there are 14 of them. And I wonder, does anyone happen to know all 14 groups of order 16? I'm offering a prize. A bottle of hand sanitizer to anyone who could rattle off, okay, without using your phone. I'll say that again for those of you born after 1990. Without using your phone, can you, no, it's kind of hard, right? Okay, maybe you know some of them. Let's just quickly take a look. There's 5 abelian. There's 9 non-abelian. These have different names, so you may say, where's my favorite one? It's called something else. Dihedral, generalized quaternion, direct product of a dihedral with C2, quaternion 8 with C2, and then a bunch of weird semi-direct products. Okay, you can derive this using advanced group theory. It's done in good textbooks, but it's hard stuff. And if you say, okay, what's that one? That one's also known as the Pauli group. Its presentation is kind of complicated. So even if we get to groups of order 16, there's an awful lot of work to find out what they are. Well, now imagine going higher. Now suppose we want to go to order 64. Well, there's 294 of those. Actually, that's not true. There's really 267. So that was one of those historical errors. This was sorted out by Hall and Senior. Actually, Marshall Hall Jr. with Senior. Yeah, so 267. No, it was, it's true. You laugh, it's true. You don't believe me, no, it was. So let's take a look at some groups of order 64. Things get kind of complicated. So there's a library called the small group library. And the first parameter tells you the order of the group. So let's have order 64. And then catalog number 2, that's an arbitrary numbering that's now been accepted. So within this library that can be found online, catalog number 2, order 64, well, it's this group. So that's the presentation. Can anyone tell me what that's more familiarly known as? Bit louder? It's not the generalized quaternion, so you have to multiply that. It looks weird, right? Multiply on the left by B, then multiply on the left by A with that, and that's telling us that AB is BA. Okay, you have to kind of get used to this. It's actually C8 squared, but it's written in a weird way. Okay, should we have another look at a different group of order 64? How about this one? What do you think the catalog number of that one is? Any ideas? You're right, it's number 66. Does anyone know what small group 6466 looks like? Well, maybe. Well, if you ask GAP what the presentation is, that's what it will tell you. It's got 3 generators and some pretty complicated expressions relating them. If you go to the personal website of Tim Dorchester, then he will tell you that small group 6466 has this presentation, which has 5 generators, but it's a lot easier to see what's going on. You see, it's telling me A commutes with B, and A with C, and A with D, and so on. It tells me, this presentation tells me a lot more of what's going on. It tells me which bits of the group are non-abelian and which bits are abelian. So we can have different presentations for the same group. This is an automated result that's correct, but it's kind of difficult to work with. So there's another problem. Okay. So moving on, groups of order 256, how many of those are there? Can't believe you don't know these numbers. Everyone knows this, don't they? It's 56,092. Everyone knows that. Okay, maybe not. There's 56,092 groups of order 256. Should we take a look at a group of order 256? Yeah. So this is catalog number 6666, and GAP tells me it has this presentation. What? Good Lord, look at that. Wow. So what is that in a more human readable form? I have no idea. No idea at all. So yes, there's a library there, but it's difficult to interface with the library. How many groups of order 1024? Well, we've known that for 20 years. The answer is 49 billion plus some. At least that's what you would have found on Wikipedia and in every graduate textbook and everywhere online until this year, when it was discovered that that is not the case. Burrell found that that is not true. And that asterisk tells us that David Burrell is a student. So what is the story here? David Burrell, as a doctoral student, at the University of Florida has overturned conventional wisdom of 20 years, determining the number of groups of order 1024. Well, this is small writing, so for those of you that can see that, take a look, and I'll summarize in a moment. But the story is this. Burrell wanted to verify the accepted number by following the method that had been published 20 years previously and couldn't get the same number. So after scratching his head, I'm making this up, I didn't say this in the paper, I presume there was some head scratching, and then he wrote to one of the authors and said, hey, there's a bit of a discrepancy, can you tell me what's going on here? And the answer turned out to be a transcription error, not an error in the computer program, not an error in the methods, but there was a transcription error. The groups of order 1024 had been determined from the groups of order 512, and right there, this number ending 54 was recorded incorrectly as blah, 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 45. So there's the source of the error. So even with all of the powerful tools we have at our disposal, this is still a super tricky area. And I hope I'm not sounding like I'm scoffing at people here. Okay, these people know vastly more about groups than I ever will. I'm trying to convince you the problem is hard, not that they don't know what they're doing, okay? How many groups of order 4096 are there? I don't know. No one knows. Unknown. So the short answer to why is this difficult is we're trying to find different sets in these groups. Well, even finding out what the groups are is going to be tough. And then, if we're going to start working with these, not only do we need to know how many and know what the structures are written down somewhere, we need to be able to have an efficiently searchable database. I need to be able to say, will you please tell me all the groups of order 256 that have a central subgroup isomorphic to C2 squared and whose exponent is no more than 32 and which have a normal subgroup isomorphic to C4 cross C2 or something like that. Okay, and I need to be able to get that quickly so that I can test out what's going on. Now we have those tools up to and including order 256, but we've only had them in terms of the whole subject relatively recently. But we saw another problem, that we can have multiple presentations for the same group, and if we want to see what's going on, we'd like to work with a presentation that makes sense for us, not one that was generated necessarily by the computer. And those are difficult to come by. And the last obstacle, I think, is if I've convinced you that the structure of groups of order a power of 4 is hugely complicated and there's massive variety, it's very reasonable to ask, why are you expecting any pattern in the existence of these goofy different sets? Why would there be any kind of structure amongst all of this diversity of groups? Well, it turns out there are some indications that there really is pattern. And maybe that's the most surprising thing of all, that there really does appear to be an existence pattern that we can latch onto. Let me show you a couple of classical non-existence results that give us some hope that there is pattern. So here is when you can't make a different set in a group of order 4 to the d. Well, when you have a normal subgroup, K, such that the quotient group is cyclic and too large. So if a group has a cyclic quotient that is too big relative to the order of the group, then provably we can't have a different set. That's a result that Turing proved working from, well, using algebraic number theory and applying it to, we'll see later, applying it to the group ring equation I showed you before. So Turing showed that you can't do it with a cyclic quotient that's too large. And Dylan, one of the co-authors, showed 20 years later you can't do it if it has a dihedral quotient that is too large. And the method that Dylan used is to say, okay, suppose we have a different set in this group with a large dihedral quotient, then we can take that different set and move it across into a different group which has a cyclic quotient the same size. So we piggyback off the Turing result. So that's an example of a transfer method. You take something that may or may not exist in one group and you move it across to another group where you know something about what's going on. So those are two classical non-existence results. The last one was 1985. There are no more general non-existence results since then, not one. In fact, there's not one non-existence result full stop since then. There's not one group in which the existence of a different set has been ruled out since this result in 1985. So you may say, okay, how many groups do these two results rule out? Well, let's take a look. So there is the number of groups, and if we apply those two non-existence results, we knock out a relatively small number of groups, only 43 of the 56,092, and we don't have a database of these, and I certainly am not smart enough to tell you how many of these groups get knocked out if I exclude cyclic and dihedral quotients of a certain size. Okay, whereas this, I can tell you because I can just throw it on the database and get Gap to tell me the answer. So how many are left over? Just subtract. That's how many we're playing with. That's the potential. And now, of these non-excluded groups, how many actually have different sets? Let's go and look at the history. So order 2, trivially, order 4 is the different set has one element, so there's no differences to take. It's kind of silly. So both of those groups trivially have a different set. Not terribly interesting. Of the 14 groups of order 16, there are 12 that are not excluded. All 12 have a different set. Whitehead and Kibler independently knew that in the 1970s. Of the groups of order 64, there are 259 that are not excluded. 258 of those contain a different set. Oops, sorry, 259 of those contain a different set. This is a historical error. This was sorted by Dillon, Liebler, Smith, and others in a collaborative project in 1990. And let me show you what was written about that last, there was something weird that just went on, that last group where I just changed the number, what's going on there? Here's a paper. Dillon has raised the question of which two groups admit different sets. The question has been settled for all groups of order 64 except this one right here with a large exponent, okay? But hey, right here, I'm showing you a different set in the group as announced elsewhere by the second author and contrary to earlier claims of someone else. Well, the second order is Ken Smith. The first order is Bob Liebler. Who do you think someone else is? So this is, yep, this is Bob's sense of humor. Bob Liebler is someone else. Okay, so Bob is making fun of himself. Bob supposedly wrote a proof that there wasn't a different set in that group, but then with Ken Smith, realized in fact that there was. Bob very sadly passed away in a hiking accident in 2009. There was a memorial conference organized for Bob, and John Dillon at that conference, 2 years later, made what he delightfully called a modest proposal. So he said, can we move on to order 256, please? He said, let's work together, we'll learn so much, let's do it to honor the memory of Bob Liebler. And the collaboration I'm talking about, the paper that came from it, this is all dedicated to the memory of Bob. So we are now trying to sort out how many of the 56,049 non-excluded groups of order 256 contain a different set. And presumably, you're sitting there thinking, please don't tell me you're going to go through each of those one at a time, trying to construct. Please tell me you have something smarter to do than one at a time through that list. Well, I think we have something a little more sophisticated than that. We're trying, of course, to deal with whole classes of groups all at the same time. But it is still the case. We're going to have a succession of filters. Okay, as long as the group does this, we have a different set. If it does this, it has a different set. And we're going to apply these filters one after the other. But when we want to know, okay, and what's left over, that's where we need the database. Okay? So in that sense, we're still counting through all the groups. It's not a hand proof yet. Okay, any questions? Any questions in the chat? So before I tell you the new idea, what was everyone else doing before? Well, most previous constructions start from this equation in the group ring, which is characterized as a difference set. And let's suppose that the group G is abelian, then this equation in the group ring, if you apply a character, a homomorphism to the complex roots of unity, if you apply a character to both sides of this equation, then on the left you're going to get the character acting on all the elements of D. Then the character applied to D of the -1 is actually going to be the complex conjugate of that first thing. So you multiply a number by its own complex conjugate and you get this character sum magnitude squared. On the right, remember that was 2 to the n times the identity. You apply the character, that maps it to the number 2 to the n. So here we have an equation which says the magnitude squared of a complex number, which is a sum or difference of roots of unity, is equal to a number, and that's where the algebraic number theory comes in. So this has to hold for all the non-principal, all the non-trivial characters. And that was how, analyzing that is how Turing proved the non-existence result for the cyclic quotient. And your group doesn't have to be abelian. If it has a large enough abelian subgroup, you can play the same game with character theory. And so that we have a recursive lifting construction that takes a different set in a group and moves to a group with larger exponent. We have a product construction that increases the rank of the group that we're working in. So between these two, we can do a load of stuff, and there's a connection there to relative difference sets using something that I'm referring to a paper that Jim and I wrote in 1997, something we called building sets. So this was, until now, this was the most powerful way we knew to construct different sets in groups whose order is a power of 2, both abelian and non-abelian, except that when all of that stuff doesn't work, when we don't have the appropriate abelian subgroup, then we have to go to some really funky stuff involving representation theory. And the difficulty there is that the representation theoretic formulation depends very heavily on the structure of the group. So you're almost down to doing them one at a time. Okay, you can't do classes of groups in the way that we'd like. You have to go really deep down into the structure of the group to apply the representation theory. So not a method that's very easy to generalize. Okay, so what's the big idea? The big idea is what we call a signature set. Let me show you an example. So let's take this abelian group. It's just C4 squared generated by big X and big Y. And now I want to write down a group ring element. Now I'm going to get lazy. So this 1, I'm writing it as 1. It means the identity in the group. Okay, so this is identity plus big X squared. So big X to the 4 equals big Y to the 4 is the identity. I'm saying here's an element in the group ring. 1 identity plus X squared times identity plus Y squared. So 4 elements if I multiply it out. Here's a second element, and I can now you can see I'm fiddling with the signs, and I'm using these subscripts to tell me whether I'm using pluses or minuses. So you get the idea. There's 4 of these. Now, yeah, so it's very, yeah, Bill asked, are they characters of a subgroup? What's going on? I'm using chi, which is screaming character, even though I'm doing my best not to say character. It is indeed a representation of the characters acting on the elementary abelian subgroup C2 squared sitting inside C4 squared. But I'm trying not to use character theory. I'm trying to stay in the group ring. Those are clearly connected with the characters, but I'm trying to not say it. I'm trying to entirely algebraically. But yes, quite right, well spotted, and that's why we're using chi. Now, those have an orthogonality property, which isn't going to surprise Bill, because he's already spotted what's going on. These group ring expressions, think of it just algebraically, they have this orthogonality property. If you multiply one by another with the -1 in the air, then if it's the same character, you get 4 times what you started with, and otherwise you get a 0. You can see this. If I multiply this one by this one, the 1 plus x squared multiplies by the 1 minus x squared, and I get 1 minus x to the 4. But x to the 4 is 1, it's the identity, so that goes away. And if they're the same, then I just get a multiple up the front. So these expressions as group ring elements are orthogonal. And now I'm going to pull out of my hat a particular 4 group ring expressions. Here they are. I'm just pulling them out of thin air. And these have a very advantageous property. They satisfy this equation. If I take any one of these aij's, I multiply by the appropriate group ring expression chi, and then I multiply by the a with the -1, I get back 4 times the character. Oops, I just said it. I get back 4 times the group ring expression. Okay, so that's simply something that I'm going to exhibit. Okay, this is something I exhibit. It has this key property, and I'm going to call that set of 4 elements is going to be a signature set on the group K, okay, on this group. And so let's just summarize what we had. The signature set on K is this property. Now, what do I do with those? Well, I'm going to define a set 4 elements B's, and they are going to be the A times the appropriate group ring element chi. And they themselves are going to have an orthogonality property. Let's just check that out. So take a B, multiply it by another B. Well, substitute in from the definition. That's there. And now this works in the same way as taking inverses of group elements, because that's all these are. So xy all inverse is y inverse x inverse. So the same thing works with the -1s in the air. We switch the order around and apply the -1. Now there's the orthogonality relation. I'm going to use it on there. We already saw that that will force KL to equal IJ, and we're going to get a 4 up the front. And then, oh look, I've got that expression, which I very carefully insisted was going to simplify. So now I can substitute in, and I'm getting 16 times chi ij. So look, the B's are also orthogonal. Okay. So let's summarize what we just learned. We have that expression for the B's. Now, let's take that K, that C4 squared, and embed it in a group of order 64. So let's start with a simple one. I want to embed it in C8 squared. So let's say that little x and little y generate C8 squared. I can embed something isomorphic to C4 squared inside there by setting big X to be little x squared, and likewise for the y's. Okay, so now that K is sitting inside my C8 squared. And now I'm going to form, here's my D, my different set, as you'll see. I'm going to form this sum. So I take the B's and I add actually coset representatives of K inside C8 squared, and I attach one coset representative to each of the B's. And what do I get? Well, we've done all the work. D times D to the -1, we want that to be 64. Well, let's check it out. Substitute in. Now we've got orthogonality between the B's. So all the cross terms are going to disappear because of this. So get rid of the cross terms. And now when I multiply a B by itself, I get this. So I get a 16 out the front, and I can turn all of these BB things into chi's. So there we go. Now, chi 0, 1 involves things with big X and big Y, which is really involving little x and little y. And that's an abelian group, so this y inverse passes through the chi. It's abelian, so all of those inverses come through and they disappear. And I'm just adding up those group ring expressions, and if you remember what they were, they are going to add up to 4, and bingo, I have my 64. So we just showed that we have, well, we're almost there. And not only have we got this, it had to correspond to a subset. So that expression D has to include every element of the group, either with a +1 or a -1 coefficient, or because of the various things that I did to get there. That's true. And having done that, we have a different set in C8 squared. Now, there's something much more I want to tell you, which is that that signature set is going to do a whole load more for me than make a different set in C8 squared. It's going to make a different set in a whole bunch of order 64 groups simultaneously. Let's see how that works. Let's take an arbitrary order 64 group, and the only condition is that it contains C4 squared, the thing on which I just showed you a signature set. It contains that as a normal subgroup. Well, then Driscoll showed in a key theorem for our work that there is a set of coset reps for our group K and G, for which this set of expressions is equal to this set of expressions. Just what we need. Okay, this is not a coincidence. We knew this at the time. It was known at the time that this was the result we needed in order to do something with different sets. Okay, so how will we use that? Well, now I'm going to construct a different set in G. So let's see how. I do pretty much what I just showed you, and this is going to come to the rescue at just the right moment. So similar idea, attach the set of coset reps to the B's, calculate d minus 1 by substituting in, use the orthogonality as before, we get the 16 out the front, and now we've got a set of expressions which we need to add up. But we just said that that set of expressions where, see, this gij to the I'm sorry, that should be inverse, not little minus 1. I suppose it's the same thing, but that should say inverse. My mistake. That gij inverse does not necessarily pass through the chi-ij because the group is not necessarily abelian. But the set of things here, this set is equal to this set. So that sum is equal to the sum of the chi's, and away we go as before. And again, because of the way that I constructed things, we do correspond to a subset, so we have a different set. So that's the idea. That's the power of the signature set. One signature set on one abelian group, and all groups of the appropriate order that contain that as a normal subgroup have a different set. And I don't have to look at the structure of the group beyond that. I just need to know, does it have a normal abelian subgroup of the right flavor? So what we showed, this is the 8 authors, this is going to appear in the journal Algebra and Number Theory. We can construct a signature set on each of these 6 groups. Okay, I didn't define a signature set. Let's say we're here, this is rank 3. It's got an elementary abelian C2 cubed. There's going to be 8 expressions chi, I, j, k with plus or minus signs. There's going to be 8 elements a, I, j, k that have to, say a, I, j, k times chi, I, j, k times a, I, j, k to the minus 1 equals 8. Chi, I, j, k, kind of obvious generalization. I haven't defined it. It's not important. But the similar idea, there's a signature set on each of those. And therefore, there's a different set in every group of order 16 that contains this one as a normal subgroup, every order 64 group that contains either of these two as a normal subgroup, or, and here's where we're really interested, every order 256 group containing a normal subgroup isomorphic to any of these 3. Okay? And I mean, we can go on. There's a theorem, I'll show you it. Okay, we don't need it right now, but if you say, did you only go that high? No, there's a general theorem. It says, okay, signature set on all abelian groups that have this kind of rank and this kind of exponent. And therefore, any group of the appropriate order that contains one of them as a normal subgroup has a different set. Kind of obvious generalization. How is that proved? It's a recursive proof. We're getting a signature set for D from a signature set for D minus 1. What are the ingredients? Well, identifying that signature set structure, something that was invisible before. People before applied the characters and just said, oh, look, the magnitude has come out right. And until we started looking in the group ring and saying, hey, there's that pattern with the plus and minuses. That factor seems to crop up a lot. There's something we can do with that. Working in the group ring has allowed us to do this. So recognizing the signature set structure, and then Driscoll's theorem that allows us to do that last tweak with the coset ramps. Those are the ingredients. And so, I mean, really, we were going back to a paper that Jim and I wrote a while back with building sets. We're refining that. We're getting, you say, where did the recursion come from? Well, truth be told, we poured through this paper and tried to turn it all into metric. But again, the computations are in the group ring, which means we have a more uniform treatment of the non-abelian groups. And you want to say, okay, how powerful was this? You had 3 different abelian groups with a signature set that was going to make different sets in groups of order 256. So how much does that do for you? Okay, so of the 56,049 non-excluded groups of order 256, there's this many that have this as a normal subgroup. That was one of the groups with a signature set. There's this many which have this. There's this many which have this as a normal subgroup. And here are, go to GAP and say, well, how many groups live in those different bits of the Venn diagram? There's the answers. Which of those numbers do we care about? It's all very fascinating stuff, but we don't actually care about any of those. There's only one number we care about. It's the one outside, yeah. It's the only one we care about is what's the complement of all of those, right? We can't have a signature. We don't have a normal abelian this. We don't have one of these, and we don't have one of those. Of the ones that weren't excluded, there's 1,416 left over. Those are the ones we need to do something about. So we have further construction methods for those. The first is a product construction. That's using something we're calling perfect ternary arrays. So very roughly, what we were doing before was a group ring element that had +1, -1 coefficients only. And now we want to think about +1, -1, and 0 coefficients. So we're allowing certain group elements not to be present when we expand out. I'm not going to go into details, but there's some kind of product construction involving some generalization of what we were doing. And that allows us to combine different sets in different groups and get different sets in larger groups. And when those are, and that's very powerful. I'll show you in a second what that does for us. And then that still leaves some over. And so we have non-systematic methods. Now, what does that mean? If you want, that is the inspired guesswork aspect of the project, or if you prefer, it's blind luck, okay? It's whatever it takes to finish the thing off. We need some methods that whatever works will do, and that's how we finish off. And these are all transfer methods. It's a way of making a different set in one group from another. There's 3 of them I can tell you about briefly. So every different set corresponds to a symmetric design because it acts regularly on the points as an automorphism group. If that automorphism group is sufficiently large, then it can contain other subgroups which correspond to different sets in different groups. So you're kind of moving from one group to another via the symmetric design. That's one method. There's the second, which I already told you about. It's the method that Dylan used to transfer Turing's non-existence result from cyclic quotient to dihedral quotient. So that's an example where there's an algebraic structure that underlines a different set in one group, and you find that algebraic structure elsewhere, and you say, oh, good, I'll copy that. This is the cheekiest one of all, okay? So GAP numbers, the small groups library numbers the groups, okay, with arbitrary catalog numbers, and then it has some method of assigning the group elements. If I say, in this group of order 256, okay, what is this element right here? Well, GAP will say that's the 57th element, okay? Now, it's using some algorithm to do that. It's using an algorithm originally to generate the groups, and then an algorithm to label the elements. Well, give me a different set in a group of order 256. That's 120 elements. Now, give me the indices, like GAP's labeling of the elements. Well, 2, 3, 14, 56, 57. Fine. Give me those numbers. And now, let me just take those numbers and move to a different group and say, is that a different set? And because of the way that GAP has done this, because there's a systematic way of generating the library, sometimes that works. Okay, again, blind luck or inspired guesswork as you prefer, but sure, whatever works to finish off. So the product construction, the first one, well, these are the groups that have a signature set. We took care in total of this many when we merged those 3 circles before. And here's how many have a different set under the product construction. And I'm showing you, we actually got rid of all of these before in the blue circle, but let's just look at the numbers. And again, you don't care about any of those numbers. What you care about is the number outside. That's the ones that don't get covered by the signature set construction and don't get covered by the product construction. And if you remember, the number that lay outside the blue circle before was 1,416, of which we've now taken account of 1,358, which leaves 58. And those are the ones we apply the transfer method to. And guess how many of the 58 we can deal with using all the transfer methods? 58, that's a little too optimistic. 57, correct, sold. 57, leaving one group. One group. Ah! Now, do you remember, okay, the last group, I'm getting tired here. The last group of order for 256. Now, do you remember the last group of order 64, the one that the Liebler-Smith paper? Do you remember that I mentioned in passing it had a large exponent? This is the so-called modular group. The last group of order 256 looks almost the same. Okay, it's got a whopping great exponent. From my point of view, not being a great expert in group theory, I think this is quite simple. I can actually work with this group. I don't know how to do all that stuff with the long relations. I can't do anything with this. This one, at least I can do the calculations. Okay, so that's the last group, the last one standing. Yeah?
So does the subscript mean that the generator of C4 conjugates the generator of 47?
That 47 is this 47 there. It's showing what conjugation by Y does.
That's what conjugation. Oh, right there.
Yeah. So it's a semi-direct product of C64 with C4, and that 47 says there's more than one semi-direct product. That 47 is that 47. So that's the last group of order 256, and the existence was determined by a summer student, William Yolland, who worked with me in 2016, an undergraduate research project. He used three things. I've mentioned two of them there: representation theory, computational search, and a vast number of emails to Jim and Ken, who at the time were in Singapore. And until just like with the order 64 case, we really didn't know what the answer was going to be until the end. Okay. So the outcome is that there's a different set in every single one of the non-excluded groups of order 256. We can fill that in the table. There it is. And you might say, now hang on a sec. You just told me that William did that in 2016. And here, you say you worked on it till 2021. What's going on there, might I ask? Well, naturally, we kept all our results meticulously over the 5 years of working on this, even though we were working on different platforms and computers in a decentralized project that researchers joined and left. There were no lost cases, there was no duplication of effort, there was no forgetting of results we'd already found years earlier, none of that. No. And then, when that very efficient, smooth process with no obstacles completed, well, then we wanted to tidy up and streamline and say, okay, which of these methods do we really not need after all, now that we've got to the end? And then we had to write and rewrite and rewrite, and there was no hint of disagreement among a bunch of strong-minded individuals about each arguing passionately for their own preferred way of presenting this result. No, none of this. So in 2021, we were done. And although getting to that result took years, you might say, do I believe any of this? Well, you really should, because you can verify this very, very quickly and easily. So again, another student, Dylan Pfeiffer, wrote a package that's been refereed and accepted into the GAP software system, and GAP is a well-trusted software system, and you can download the online database that Ken has published, and it took me 20 minutes on a 9-year-old desktop using a standard implementation of GAP to verify that each of those sitting in there is a different set. So you should certainly believe our result. Okay? If you think that well, I'm sure we've missed tons. If you want to play with this and try to look for patterns that we have not yet spotted, this is online. You can find a link in the paper. By all means, please play with it, see if you can spot things that will help. So, time to move on, right? No, please, no, I can't cope. Okay, there is not a database of 49 billion groups of order 1024 yet. There might be soon. I really hope that before that happens, we will have better tools than saying, let's just go through these things one at a time and see after a succession of filters what's left over. Okay? So I couldn't even tell you how many are left over, let alone go through them. But I'm sure you've noticed this, and there's a very natural question. Like, is that all we need? These are necessary conditions. Are they sufficient? Now, this is like a personality test. This is like one of those ink blot tests. Okay, so I determine your personality type by seeing whether you're saying, oh, of course there is, or are you kidding me? Why would you think that? So the optimists are saying, now come on, it's like you've gone through, with excruciating effort, tens of thousands of groups with this incredible variety of structures. And at the end of that, in every single case, for orders, I mean, forget order 4, that's trivial. Order 16, order 64, order 256, you've got more patients than I have. And in every single case, you've got a different set. I mean, it's kind of obvious which way this is going, isn't it? But if you're a pessimist, you're going to say, okay, you have a result for d equals, forget d equals 1, it's trivial. You have a result for d equals 2, 3, and 4. That's the 3 smallest integers. And you want to generalize to all d from that, really. And you just told me that the number of groups at the next size up is going to dwarf all the ones that you twits have tested up until now. It's like, there's barely any evidence to go on. So we've actually had that discussion amongst ourselves. It's not important who thinks what, but even amongst the authors, we've got different opinions as to which way that goes. So what are we going to do? Well, we're not going to just go through order 1024. Like I said, we couldn't if we wanted to. And we certainly can't go through order 4096. We don't even know what the count is, let alone what the groups are. So where are we going to go from here? Where I want to go from here is to go back to orders 64 and 256 and say, can we do that by hand, please? It was nice that we had theorems, but there was computational searching going on to apply. I hid it, but the product construction involves a lot of computational search. And some of the transfer methods are just kind of magic. It's just tricks and anything will go. Those can't be repeated. That was just whatever it took to finish the problem off. So you might say, how about we have a proof for order 64 or 256 that does not rely on saying, Gap, will you please tell me all the groups of this order that have this, this, and this, but don't have one of those? Just good old-fashioned hand proof. Okay, I'm almost done, but can I just point out that yesterday we had a talk on cooling codes, followed immediately by a talk on something called frost. And I propose that we're going to all chill out and celebrate Doug 66 with a rendition of the well-known birthday song, Freeze a Jolly Good Friday. Okay, thank you for your attention.